Hi there. Thanks for joining me. My name is Michael Petrovich. I am a people analytics manager. That's what I do for a living. And probably most importantly, though, I'm also a student of the Applied Data Science program at Bay Path University. The My presentation for today really centers around understanding gender pay equity through adding additional statistical techniques that we normally wouldn't see in your standard pay equity analysis approaches. But before I dive into the meat and potatoes of the analysis, I think it's important to cover how pay equity analysis originates, or really any type of pay equity problems originate. And that is really through the compensation methodology. Um, I would say that for the most part, mid to large scale firms, with respect to their revenue, but also the amount of employees that they employ, they usually have a compensation leader. This compensation leader is either going to sit in HR, or they're going to sit in finance or legal. Anyhow, really, what one of their main responsibilities is to develop and implement, either nationally or globally, a compensation framework that is going to benefit both the company and the employee. So it has to have the right balance in terms of compensation, where the company is going to be profitable. So, for example, it's not going to be paying employees more than it brings in, because that's just a recipe for disaster. But it's also going to pay employees at a rate to where it incentivizes the employee to stay with a company. And that's important because ultimately people do leave because of pay, because of opportunities. Although, yes, some stats show that employees leave because of culture, maybe the right culture fit, maybe poor benefits, or maybe a not the best relationship with management. One of the things that is within the control of the company to to manage is compensation, and how it incentivizes employees to remain with the company. At the end of the day, operational costs per turnover are way higher, so it costs more to lose someone than it does to retain someone, right? So it's just good strategy. Also, part of the framework should drive towards pay equity, which really means that out of all the variables that play into pay, so for example, maybe the level of education, the years of experience someone has, the industry where they come from, um, gender or race, ethnicity, for example, should not play a role like other variables play a role, right? So part of the pay equity analysis is first to make sure that the compensation structure actually is working, or uh, two, that it's actually implemented well. Because one thing is for it to be developed, the other thing is actually to be executed by management. And then the other factor is really to understand if the the variables that are supposed to influence pay are influencing pay. And variables such as gender, like I mentioned earlier, or race, ethnicity, that should not be influencing pay, to make sure that they remain that way. If by any chance the statistical analysis shows that there is an association between, for example, gender and pay, well, that's a problem, and that's certainly insightful for the company to understand, so they can begin taking steps to solve for that. So, something else that's extremely important to cover here is that the analysis that I set out to perform really revolves around interpreting the best model. In other words, understanding why something is happening and not necessarily worrying about the prediction accuracy. And that's really important because from a data science standpoint, it helps give the data scientist direction, to whether we're looking to implement algorithms that help us understand the model better, or we're looking for models to help us raise the accuracy score. In this case, we're not really looking for that accuracy score in terms of prediction. We are looking to get an understanding of the parsimonious model, so then we can take these insights and actually be able to interpret and describe them to business leaders, so then business leaders can do something about it if something needs to be done. So Speaking about the opportunity, the main reason why I set out to do this entire research and analysis was really because I noticed that there was a bit of a flaw in the standard pay equity analysis approach. The flaw comes in kind of two flavors. One is that I wouldn't really necessarily call it an analysis because it takes probably less than 5 minutes to do this. But there is a metric that is called the unadjusted pay gap. And all that metric really does is that it speaks to the ratio of the difference in pay between males and females. And the way this is calculated is by taking the average of male pay, subtracting the average of female pay, and then dividing that by the average of male pay, right? At that point, you get a ratio. However, that doesn't really speak to all of the variables, all of the attributes that go into why someone would get paid a specific amount, right? It doesn't speak to education. It doesn't add that specific control, or it doesn't speak to location. Location is important because if you're really looking at the difference between different states, perhaps the same job title, right? But different states, one thing to understand about location is that the cost of living in New York is completely different and way higher than the cost of living in Dallas, Texas, for example. So you would expect for the same job title, the same job level, regardless of gender or race, to be paid differently. Um, the other flavor of pay equity analysis is more or less what we're going to explore more of, which is your multivariate regression. And that's typically called the adjusted pay gap because you're adding controls to adjust for anything and everything that should be included in terms of its impact on pay. The flaw in this, or the gap, is that many analysts just stop at plugging in all of the variables and not performing any subset selection. So at the end of the day, what you end up with is all of the variables that you wanted to model, not necessarily what the model actually should be with regards to the outcome of pay. So what I wanted to do in this research, right, or this analysis, was to add or improve the analysis by including data mining techniques, both supervised and unsupervised. So there's a series of steps that I'm going to take here in the next 30 minutes, I would say, and it all starts with exploratory data analysis. But before I go through these steps, I want to make sure that I cover the basics in terms of the data set that we're dealing with. For starters, the data set that I used is a synthetic data set, so it's all dummy data. It was sourced from Kaggle and includes roughly 1,500 observations, about 33 variables. I did not use all 33 variables, however. The variables that I did use were income, gender, education, years of experience, tenure, age, department, job level, job role, which in other companies may be called job title, location, and whether the job includes business travel or not. So you'll notice that's not a total of 33. Those are, however, the variables of interest that you're going to see in most pay equity analysis. The other variables that we see in the Kaggle data set really have nothing to do with pay. So for example, a good chunk of those variables that I did not include here are based on survey responses, dummy survey responses for that matter. But again, surveys don't have anything to do with pay, so at that point you don't need any fancy data science to rule out those variables. You just go ahead and rule them out based on logic. Something else that I want to cover is that technically I used monthly income. All right, and I also added a natural log of monthly income, so I'm ending up with two variables for monthly income. So with regards to monthly income, yes, you could use annual, you could use monthly, it's or quarterly, is up to you, so long as obviously the rest of the observations are the same, have the same type of income. And with regards to taking the natural log, the purpose there is, one, it certainly helps normalize the data. typically, eh, typically for the most part, you're going to notice that salary information is skewed, because of course there's going to be a lot less people uh, with higher salaries, right, than with the bulk of the workforce, which is um, job level 1, 2, and 3. So with respect to that, taking the natural log is going to center the data, or not necessarily center it, but give it a normal distribution. Also, probably most importantly, too, is that by taking the natural log of income and regressing on income, your coefficients are with regards to the results, they're going to approximate the percentage change in salary, and that's really important because at the end of the day, it's a lot easier to interpret that way. Also, we're not necessarily looking at differences in terms of dollars. We're looking at differences in terms of percentage. So again, easier interpretation from that standpoint. Okay, so with respect to the steps that we're going to go through here, again, we're starting off with exploratory data analysis because it's extremely important to always get to know your data, explore it before you do anything fancy with it. Ultimately, it's really going to help guide you anyhow with regards to the types of more advanced approaches that you're going to take. So we'll do that first. Then we're going to progress onto hypothesis testing. There are some questions that we can't answer with exploratory data analysis, so we can tackle those with hypothesis testing. The same goes for multivariate regression. Same goes with subset selection and regularization. They're just methods that build on one another to improve or optimize our analysis and ultimately end up with a superior outcome, or being able to interpret the truest model. We're also going to look at some unsupervised learning techniques that are going to help us to understand or get more out of our analysis. So principal component analysis is going to be one of them, specifically using biplots. I'll show that later on. We're also going to go through association rules, some interesting association rules that may not really tell us much about pay, but will tell us about some of the quote unquote rules, right, associated with specific genders in this data set. And then we're going to wrap it up with a look at a Bayesian network using our final model variables to understand how they play together in the same sandbox. So with that said, on to exploratory data analysis. This slide is probably going to have what I would call, at least from my standpoint, some of the most important results from exploratory data analysis. The first one being the pie chart, right? So we have that split between male and female representation. Females make up 40% of this data set. Males make up 60% of the data set. From a department standpoint, we'll notice that it's about even in terms of the distribution between departments in that regard, but between gender and the departments. But when we look at the departments themselves, we'll notice really quickly that research and development, that includes 65% of the population, right? Sales is going to include 30%. So between sales and research and development, we really have the bulk of the data set, which means that the last department being HR, only consisting of 4%, it's gonna probably it's a bit of a concern, or at least a back pocket to think about later on, because we don't have too much representation there, especially perhaps later on when we run statistical analysis, and this may throw a bit of a curveball, or perhaps not. Gender by job level, over to the right, the bar chart. What we notice here is that ultimately, there doesn't seem to be too much difference, right? When we think back at our 60-40 split. in between jobs level 1 through job level 4. So in detail, job level 1, what that means is your entry level jobs. This being probably more professional type departments where you may need a degree. I would say that these entry level jobs, for example, an analyst would be a perfect example of job level 1, where on the other side of the spectrum, job level 5, well, that's going to be your VPs and C-suite level, right? So your chief executive or your chief officers. So yeah, I don't notice too much of a difference there between job levels 1 and 4. However, I think job level 5 may suffer a little bit from underrepresentation from a female standpoint. So while that doesn't really speak to pay, which is ultimately what we're after, it does bring an insight that you could technically take over to the recruiting department and say, hey, look, we may have a little bit of a underrepresentation problem here. So whenever one of these positions does come up open, perhaps you can take a look at a completely different candidate pool, right? And just not do the status quo to see if we end up with a more diverse candidate pool for those jobs and attract more females in this case. Now, actually, let me go back. With regards to the income, though, right? So for females, going back to the pie chart, what we notice is that the average income is for females is 6,687, which is slightly higher than the male average monthly income of 6,381. So that gap is about 4.8% less for males. And right there, that's where like our initial insight. Now, this is of course based on this synthetic data set from Kaggle. So you may see it differently if you ever run this analysis in a real world scenario. So that our first question would be then: is this gap explained, or is it significant? So we're just going to bench that question for later on. We'll be able to answer it through our analysis. Gender pay by department and job level. So this visual here then is taking our last slide, right, putting it all together, and taking a look then at the income between gender and the department. And what I see here, for the most part, is not much in terms of insights, which I guess technically is an insight. What it's ultimately telling me is that, yeah, there are some departments where males, both departments and job levels, where males bring in slightly more or earn more. But inversely, then there's other departments and job levels where females earn more. What this does tell me, probably on a side note, is that if I were to get a job in this synthetic company, I'd probably apply at sales because they seem to be bringing home the bacon a lot more. But other than that, we move on to our next exploratory data analysis visuals. We're going to look at gender by tenure band, right? So no insight is still an insight. Really what this tells me is that we're not losing any specific gender based on tenure. So the inverse of tenure really is just turnover. So what we're looking for here is making sure that, for example, in 0 to 4 year tenure band, that we don't have a lot more males than we have females. Because what that would mean is that recruiting may be trying to build a pipeline of diverse talent, but somehow we're losing them, where the company isn't aligning to their needs and they are jumping ship. So over to the right, what we see is job performance scores by gender. And again, no insight, but then again, that's insightful. What this is telling me is that ultimately for job performance score 3, 3 is defined as it meets expectations, and 4 is defined as exceeds expectations. Ultimately, what this tells me is understanding the 60-40 split, this is the same. So ultimately, it's not like there's a specific gender performing better than the other gender. Performance, of course, is associated with pay, but we're actually going to remove it from our future modeling because ultimately we're in order to include performance, you would also include historical performance, which the data set does not include. Okay, so thinking back at our unadjusted pay gap of negative 4.8%, meaning that males earn about 5% less than females, according to this data set. What we notice here from a box plot standpoint is that there are a lot more male outliers in monthly income at the probably the top job levels. All right, we noticed that earlier in our representation, but we do have slightly broader range in the female box plot with regards to that monthly income. So the question is, okay, we know the unadjusted pay gap. Does the effect of gender impact pay? And what we can do to answer this question is to run a two-sample t-test, right? Taken male and taken female. In order to run the two-sample t-test, we do have to understand if it's equal variances or not. So in order to get our answer for equal variances, we run a Levene's test for homogeneity of variance. We end up with a p-value of 0.71, so we cannot reject the null hypothesis. So we move on to the two-sample t-test, and under our criteria or parameters for equal variances, we identified as true. And our outcome from the t-test tells us that it's a p-value of 0.22. We're looking for a p-value of less than or equal to 0.05 in order to reject the null hypothesis. So we can't reject the null hypothesis in our sample. So technically speaking, our sample does not provide sufficient evidence to conclude that the effect of gender on pay exists. So in other words, even though we showed the unadjusted for 4.8, at least from a t-test standpoint, we can conclude that pay is equal. It may just be that variance that nudges a little bit of that skewness. So we also want to look at interaction plots because we're getting ready to take this up a notch and go beyond t-test and go into ANOVA. But before we go into ANOVA, let's look at interaction plot between job level and gender over to the left, and then an education and gender interaction plot. And what we notice with both is that there isn't any interaction. The only somewhat odd result here with that slope, a rather large slope, is on education level 5. But really what that means is that in terms of PhDs, we may see that female PhDs get paid slightly more than male, but that could just be due to other differences or other variables. All in all, there isn't an actual interaction per se, so we can move on, stating that there's nothing really to gain here, or any red flags. Okay, so looking at further exploring the question of education, right? Because we noticed that education level 5 was a lot higher for females than it was for males. When we plot that here, if we go all the way to the right and we look at female and male 0.5, which just means education level 5, what we notice is that there is more of a spread with female PhDs on monthly income than there is in males. Okay, so that rather large spread relative to males is most likely going to have an impact, and why we saw that interaction or that somewhat steep slope there in our interaction plot. So with that said, we're going to move on to ANOVA. We have to do the ANOVA in R. As much as I'd love to keep going on slides, I think it's going to be a lot more engaging for all of you to follow me in R. So let's do that. So running the ANOVA in R, what I'm doing is just going back to the variables that we plugged in earlier in our interaction plots that we technically explored, which were education, job level, and job location as an extra one, and gender, right? And of course our Y variable, our outcome being monthly income. So let me run this. Okay, so once we run the ANOVA test, what we find is that gender, let's look at the bottom here, these are going to be the results. You highlight these. For gender, we find that to be statistically significant variable. Same thing with education, same thing with job level, not so much with job location. All right, so that's an important finding right there with regards to job location. It's also an important finding to understand that gender in this particular model does play a role. But we want to technically plug in more variables than that because our compensation philosophy includes additional variables. So what we're going to do is we're going to skip to model number 2, which is going to allow us to plug in the human capital controls. Those are going to be male, the gender, of course, but adding age, education, years at company, which is tenure and total working years. And once we run that model, what we find is that gender is no longer statistically significant. What are statistically significant are years at company and total working years. All right, so I think that's insightful there. We've technically flipped the model or have changed it. We're going to change that one more time. What we're going to do in model number 3 is add an additional layer of variables, and these are going to be the job-related attributes. So the department, the job level, the job role, business travel, etc. And here, it's a much bigger model, first of all, so our view is going to expand. What we find is that male is, gender, the gender attribute, is not significant. The ones that are, just to skip to the important ones here, are total working years, makes sense, job level, job role, and business travel. Somewhat. I think business travel starts getting a little lost there. But ultimately, that starts telling us, okay, these are really the variables that are impacting or associated with our outcome the most. So let me pause here with regards to the analysis, and let me just say that at this point, the standard pay equity analysis kind of stops, and there's no subset selection done. The problem with that is that you're really at the mercy of this particular model being the truest model. There is no testing that has been done, right, to confirm that. So what we're going to do is, by taking it a few steps further, we're going to leverage subset selection and regularization to find that best model, right, that explains our outcome. And thus, by doing that, we'd be taking this a lot further than typical practice. All right, so let's see. Let's do just that. We're going to start off with computational subset selection. We're using the GL multi function in R. There we go. And some of the parameters are, first, the exhaustive approach. All right, so we are using the exhaustive approach. We're not using the backward or forward subset selection. This is going to give us the most amount of variable, I'm drawing a blank here, the most amount of variable combinations, and therefore really explore every single combination out there and land at the one that explains the model best. And the criteria to do that is based on AICC. Okay, So that is a Kaike information criterion. I'm drawing a blank on what C stands for, at least for now for this presentation. But ultimately, it's technically taken in consideration that this may be a sparse data set at the end of the day, especially with some of those departments that are underrepresented. So that's one of the main reasons why I used AICC. And AICC, if you're not familiar with it, is really an estimator of out-of-sample prediction error. So all in all, is going to help us select the best model. All right, so as we do that, I'm going to run this really quick. What we find is, compared to our model, our third model earlier, we end up with a much easier interpretation of the parsimonious model. So now our variables of interest are job level, job role, business travel, and total working years. All right, so 4 variables. And now we're making really some traction here. Let's see if we can. Okay, I was going to try something, but let's go ahead and move on because of time. The next algorithm that we want to run is lasso regularization. All right, and lasso regularization is going to take a different approach to finding the best model. It's going to penalize variables. It's going to first of all find that penalization, which is the lambda, and it's going to do so by plugging in a series of variable combinations. And what we end up with is going to be essentially our best model. All right, so here we have the algorithm at work, and it's identifying the lambda, essentially, and how many variables are going to reduce the mean square error right at the elbow, if you will. But really what we're interested again is that coefficient. So let's take a look at what that model is, what it has landed on. So what we have here is the new model. So I know I'm going model after model showing coefficients. So if your head's spinning, that's okay. Mine was as well. And remember, what we're doing here is we are going model after model, right? Just to draw comparisons between their performance. Because at the end of the day, what I want to showcase is the difference in performance between these models, to be able to select one, like moving forward, to end up with the best model interpretation. So Lasso is going to say that age, years at company, and total working years are important. It's going to drop gender. So technically speaking, at this point, from the concern of the business, right, we could technically walk away and say, yep, gender continuously falls off, both subset selection and lasso regularization, so we're done. But we're not going to do that, because what we're going to do is, one thing is to understand that gender doesn't really play a role. The other thing is to find out which underlying model really gives us the best description. So we'll keep going. Education seems to have an impact here, job level and job role as well. One of, I guess, a flaw or just something that can be optimized from this lasso output on coefficients is that you'll notice that some variables that are technically grouped together, it removed some and it kept others. So for example, if you look at job location is part of the same factor, but it dropped 2 of those levels and it kept 1. Which is interesting. And then the same thing goes with like stock option level. And because of that, what we want to do next is actually run a similar lasso that is called group lasso. And the group lasso is going to allow us to format, I guess I would call it format, but group the variables that need to be grouped That way, the penalization can actually be implemented or carried out on groups of variables. So when we do that, when we run the group lasso, what we end up with is a much cleaner version of the lasso output that you just saw. There we go. And let's just focus on, it's easy to pick out the ones that have been dropped because they're all 0. So let's just focus on the ones that are not 0. Those are going to be age, which is pretty small. I'm not sure if I would really count it in. It's years at company and total working years. It has completely dropped gender, education, and department. We see job level again, though, just like we saw it before. We see job role, and that's really about it. It also dropped business travel, job location, stock option. So a much simpler model that is going to explain our output a lot better ultimately. Because what we really end up with is 4 variables: years at company, total working years, job level, and job role. All right, so at this point, technically, we're done. We could say, hey, look, we've got the best, absolute best model. Right? We took it further, we optimized, and we've identified the variables that play a role here. But just to leave no stone unturned and make sure that we do have the best model, what we're going to do is compare AICC to, let me make sure I've got it. 4. We're going to compare AICC against all of the models that we've run before. Oh, model 1, gotcha. Give me a second and let's run model 1. Okay, so model 4, model 3, model 2, model 1, so in that order, top to bottom, what we notice is that our last model, our group lasso, performs better than any other model that we've done before, right? So at this point, we know that our group lasso reduces AIC to negative 214. It's really our lowest one when you compare them to other AIC values. It's rather low anyhow. So at that point, we could say, okay, well, going forward, we're going to really skip the manual modeling. We're going to even skip exhaustive search. We're going to just go with group lasso, right? And to identify the best model. So that concludes the model selection, the feature selection. What we want to do next is learn a little bit more about our data set. So at this point, we're going above and beyond, but it's really for the cause of learning more about how our data is behaving. One way to accomplish this is through principal component analysis, specifically a biplot. So what I'm going to do is pull up the biplot of our PCA on our data, and I'm going to go over about 3 different findings that I found insightful. One is that these clusters here, which kind of run horizontal, those are mostly influenced by department. All right, and they're going to influence principal component number 2. The other insight is with regards to eigenvectors. Right? So if we look at gender, something important to note is that gender is the complete opposite of job role and department. So it is negatively correlated to job role and department. Right. Something else to consider is that with regards to these angles here, gender is almost at a 90-degree angle compared to total working years, years at company, monthly income, and job level. So gender is really not associated at all with monthly income, but we notice that it's not really associated at all with like total working years or years at company or job level, which means that you don't have to be male or female to be at a specific job level necessarily. You don't have to be female or male to have certain number of years at the company. And some of that may be pretty obvious. It may make complete sense. Why not, right? But I think the most important aspect here is that it doesn't really have anything to do. It's not correlated at all to monthly income. So that is what a PCA biplot can tell us. Really, how our data is when you crunch all of the dimensions that we have into two components, and we retain all that variance that PCA allows us to retain. It helps us understand how the variables are playing together. The next step is running the a priori algorithm, right? And the a priori algorithm, I thought one of the best insights, so I'm going to go straight to it, was the association to females. And although there's no really association to pay because we're not running it by pay, what it does help, I think, is it helps point at something we saw earlier in our exploratory data analysis that we could technically take to our recruiting department. So let's inspect the associations to females. Let's wait here while it loads up. I thought this was pretty interesting. So education, when we look at female, male equals 0, that's going to be your female factor or level. We notice that, let's see. There's not much representation of females in Department of Sales, not much representation in executive leadership, right? We noticed that earlier in our EDA, at least executive overall. And there's not much representation of female in terms of not having a lower education, right? So high school only. What we normally see is that females in this specific data set have bachelor's, master's, and PhDs. But with regards to the representation, we just noticed a few things here that say, okay, well, maybe there's something to be said about doing a better job at what word am I looking for? At attracting better talent, right? And a more diverse pipeline of talent overall that is going to help with representation. One thing that comes to mind is if we don't really see the right representation between departments in terms of gender, what makes us think that it's the right representation in terms of race, ethnicity also? So last but not least here is, I saved the best for last, is the Bayesian Network. And the Bayesian Network, what we'll see through a visualization, is that it allows us to understand, or better understand, how our input variables, the conditional probabilities between our input variables. So we're used to seeing the input variables only support, right, the association to the output. We're not really used to seeing them associate to each other. And what a Bayesian network allows you to do is really explore the truest model, I would say, which in this case, what we see is that monthly income is predicted by job level. Job level also predicts total working years. I guess you could technically flip the direction there and say that total working years predicts job level, but job level also predicts job role. So we see job level as kind of like the basic, or no, maybe not the basics, wrong word. The main node that influences other significant nodes, right? Like total working years and job role. And much like to our earlier models, we see that stock option, gender, business travel are not really part of this network at all, as they're on their own. They've got no vectors pointing towards them or pointing out. In this case, again, yes, we would be interested more in gender, right? Because it's a gender pay equity analysis. But ultimately, it does help to understand what the other variables, how the other variables play a part. All right, so with that said, that really concludes the analysis. I wanted to wrap this up by just reviewing what we've learned so far. And I won't make it complicated because we've technically covered a lot of numbers, a lot of complicated stuff. So overall, what we learned is that we can certainly improve our model by implementing group lasso. All right. So group lasso seems to have a home when it comes to pay equity analysis. The other thing is that unsupervised learning approaches help understand patterns in the data set, and they may speak to what we've already found in EDA, but I do think that they add more of a robust twist to our insights. That you're going to walk away with a bit more understanding at the end of the day. So it pairs up well with EDA, but a lot of times I've kind of figured, well, why not run unsupervised learning first as part of my EDA, and then run the supervised modeling. So in this case, I kind of did it backwards, but if I were to do this again in the future, which I'm pretty sure I will, in a real world setting, I would actually add unsupervised learning techniques like PCA and Bayesian networks up front as part of my EDA protocol. And then last but not least, the data mining improves results and interpretability of patterns in the data. So we saw that. We noticed that it took whatever our third model was, right, with human capital and job attributes, and it really blew that up by looking for the absolute best mixture of variables. So I would like to thank you for your time. I appreciate you joining me. I will be including my contact information later on as part of this presentation. If you have a question, feel free to reach out, or if you just want to connect, you can reach out as well. Thank you. Appreciate your time.